Well, obviously, first of all, I have to thank Álvaro and Gonzalo for inviting me to talk here today. I prepared something that might be maybe too specific compared to what our previous speaker has been telling us. Anyhow, I'll try to give it as a touch as general as possible. Basically, I'm going to talk about the optical design of mesoscopic solar cells, which are basically dye-sensitized and perovskite solar cells, although I know there are some other cells that can be considered mesoscopic. But I'm going to use these two examples to highlight probably, if not all, most of the approaches based on photonics that are being used or have been used in the last years to improve the efficiency of solar cells. First of all, well, I'm going to skip this actually because this is what I just said. What is the key reason why we want to work in nanophotonics or photonics in general in a solar cell? Although this might be pretty obvious for everybody, I wanted just to rethink this a little bit. From a very basic point of view, very basic perspective, a solar cell is just a device who has a mission of absorbing light, using that light to generate photocarriers and collect those carriers, right? So in this very basic description, we find the central idea on which the use of nanophotonics in this field is based. Because if we want to have high absorption, we typically will need to have thick materials. We need the light to go through our material for a while, in our relevant length, so we can absorb this light, so we can absorb these photons. At the same time, if the material is thick, the charges we are going to generate will have to travel longer to reach the contacts. And it's in this compromise when we find the balance in which nanophotonics can play a role, right? Because we need to have materials that can be as absorbing as possible with the minimum thickness we can get, so we can collect charges efficiently. This is a key issue for certain fields, like, for instance, organic solar cells. It is also for dye-sensitized, and it is much less for silicon, for instance, or other solid-state semiconductor solar cells. So one of the things I would like to discuss today here is if it's really, are we really getting somewhere in this, with this idea of improving the efficiency of solar cells using photonics or nanophotonics? Well, there are a few strategies that can be, maybe there are some others I'm missing here, but I think the main ones you will find in the literature, if you look for optical design of solar cells, will be the obvious one, which is to reduce entrance reflection. And this is used in all sorts of photovoltaic devices in general, is to use an anti-reflective coating, right? So I can get more light within my cell so it can be absorbed. Then, to increase the optical path, right? I need to increase the path that my photons travel through my absorbing material, so there's a higher chance of absorption. Another strategy very related to this one is to increase the time of flight. So maybe I can try to couple my light to very slow modes, so I increase the radiation matter interaction time, and by this means I can also improve the probability of absorption. And then I can increase the optical field. I can localize light where I want it to be absorbed. And this is obviously the realm of plasmonics, which has been discussed and used a lot in the last years in the field of photovoltaics. How do we tackle this from the point of view of material science? So what are the materials that can give us this, a solution to these different strategies or approaches that I just mentioned? Well, one that is the first one I want to mention is texture surfaces. Texture surfaces serve as anti-reflection coatings. They give us light diffusion if they are randomly textured. They give us diffraction if they are ordered, right? And also we can even get enhanced near-field effects because actually both with metals and with dielectrics, right? So texture surfaces are actually the one or the method that is being employed the most to improve the efficiency, and is the one you can find in commercial solar cells. And even in research is one of the most interesting approaches because it gives a very high efficiency. Then we have plasmonic nanostructures, and by these we have a wide variety of structures that go from simple metal particles to actual nanoantennas or more sophisticated things, right? And in this case, we get both an enhanced near optical field or scattering that we can use to increase the length, the path length of light inside my absorbing material. Then we have an approach based on photonic crystals of all dimensions. And in this case, we have a wide range of effects that can be useful for a solar cell, like slow light propagation or increased or diffraction, specular reflection even, enhanced near optical field again. And finally, I identified disordered bulk materials in which we make use of multiple scattering, so light gets somewhat trapped because of multiple scattering inside these materials. Okay, so what I'm going to tell you today is about mesoscopic solar cells and how all these different approaches can be used to improve the efficiency. But before getting to that point, I was trying to find, and I was surveying the literature in the last years in the Web of Science, trying to see how many papers are published in this field, nanophotonics for photovoltaics. And I couldn't do it. Because if you write photonics or nanophotonics or plasmonics, or you get more specific, graphene, carbon nanotubes, and combine it with photovoltaics, you always get a lot of papers. And if you start analyzing them, most of them don't talk about it really. They are just mention it because it's fancy, and it's somewhere in the abstract or somewhere in the keywords, but they did a completely different thing. So I couldn't bring here a list of papers in the field. Probably if you get, you have a long time, you can do it, obviously, but it's surprising how you use these words, and most of the papers you find are not related at all, right? So I could identify clearly one field in which nanophotonics is making a difference, and it's this one, thermophotovoltaics. It's an unknown field for many people because the efficiency that has been got until a year was just 1%. However, the concept is extremely interesting. It was proposed in 1979 by Richard Swanson, an engineer, who said that, okay, we have the PV cells we have, right? So we are going to have an external quantum efficiency, and we are limited by that. And we have the sun we have, right? So what we have to do is try to make these match these, right? So what we need is materials that can absorb all this solar spectrum. So I'm looking, he was foreseeing or wanted to use materials that have this sort of absorption or absorptance, right? So basically it's one in a huge spectral range, and that then all that heat is converted into emission, an emission that coincides with my external quantum efficiency, right? So this is in very few words the key concept on which the field of thermophotovoltaics is based. People have been using different materials in the last decades trying to make this dream come true, and as I said, the result was 1% efficiency. So it's very, very inefficient. However, in the last years, people working in the field of nanophotonics starting devising materials to get this an efficient absorption and conversion of, to get an efficient thermal emission. And in this year, 2014, the group of Evelyn 1 in the MIT got a 3.2% efficiency, which obviously is low. But you have to think that once nanophotonics have entered this field, we have a triple value than the one we had before. And this is something that nanophotonics hasn't got in any other field in photovoltaics. So there's only, in this case, where nanophotonics is the key to high efficiency. In all the rest I checked, nanophotonics is okay, it helps. All solar cells have some sort of optical design, basically based on texture surfaces, and not plasmonics or photonic crystals, right? But in this case, you need photonic crystals, you need advanced materials, right? So it's I wanted to bring this as an example, and I'm not going to talk more about that, but I think it's the only one in which we can say that nanophotonics is making the difference with respect to the previous technology. Having said that, I'm going to start talking a little bit about the mesoscopic solar cells. And the first one I want to discuss, which is the one I have been using as a platform to test different optical materials, is the dye-sensitized solar cell, which is basically a cell that is a thin film, and a thin in this case means around, well, from 2 to 10 microns, depending on how you prepare it. And it's basically made of titanium oxide, nanocrystallites of titanium oxide, that are sensitized by this dye. These small violet dots are a ruthenium dye, or there are many other dyes that are used today. This dye is actually in charge of harvesting sunlight. And those excited electrons are transferred to the titanium oxide, which is behaving as a wire that takes the charge to the metal contact. One key feature of this cell is that everything has to be embedded in an electrolyte. So all this film is porous. So the electrolyte can get everywhere. The electrolyte has the mission of taking charges here and transporting them to the dye so the dye can be recovered. So there's a regeneration of the dye thanks to this flow of electrolyte in the system. The electrolyte can be solid state, can be liquid state, right? And this is basically the path of charges when sunlight gets into the cell. Well, this cell has a record efficiency of 13% approximately, right? So it's well below silicon or other approaches. But it has some interesting features. One of them that was identified from the very beginning is the transparency, right? So actually, this is a cut that we observe in the scanning electron microscope of the standard electrode. And this is the nanocrystalline titania, and obviously as grainy as it might look here, this is a completely transparent material. There's no diffuse scattering. And once you sensitize with the dye, you get a certain region of the spectrum that is absorbed, but in the red, light is transmitted, so you get this reddish color. That depends on the dye. You can use many dyes, and actually, this is a picture taken a few months ago by my students in the HOPV conference, which is focused on dye and perovskite solar cells, that took place in Lausanne. This is the conference center of Lausanne. And all these things you see here with different colors are dye-sensitized solar cells, each one sensitized with a different dye, right? So this is one of the first examples of installation of a photovoltaic window based on this dye-sensitized technology. Well, as you can see, well, this is obviously one of the advantages of dye sensitized, if you want, or one of the added values. However, these added values are never enough to justify the full technology, so people try to improve efficiency in these materials from the very beginning. So this was, let's say, the basic material in which you have your glasses in blue. This is your nanocrystalline titania with dye, and this is the electrolyte embedding everything. And okay, light inside this film just propagates ballistically and at a certain point gets absorbed. And that probability of absorption depends on the extinction coefficient of the dye. So what the two approaches that people have been using is to include diffuse scattering particles inside the film, or diffuse scattering layers at the back of the film. So a diffuse reflector, or a strategy based on multiple scattering. Okay? In the two cases, you get much better efficiency, but particularly in this one. So there hasn't been any record cell in the last 10 years that didn't have these designs. Okay? So in this case, the optical design is also key. Without this diffuse scattering layer, you don't get the record values, right? But what happens? Once you put a diffuse scattering layer in the back, you lose your transparency. So one of your added values is lost, right? Okay, so this is basically what you get if you analyze transmittance of the standard device or the device with a diffuse scattering layer. These are experimental data. You get much better efficiency, but you lose completely your transparency, right? And now I'm going to tell you a little bit about what was our approach to this field. And a few years ago, we decided to try to create materials that behave as reflectors, as mirrors, in selected spectral ranges. And this is basically a Bragg mirror in a new, using new categories. This would be a one-dimensional photonic crystal. but in which all layers were porous. Because, as I said before, you need the electrolyte to flow through anything that you include in this device, right? So these mirrors would allow the electrolyte to go through it. So in a sense, it's a porous mirror that not only gives you high reflectivity, but at the same time, it allows gases or liquids to flow through them. This, actually, we develop it using techniques that can be scaled up, and you can get pretty large areas with very high uniformity. And the spectral range at which you reflect depends exclusively on the thickness of these layers, right? So I'm going to make this long story short, because we have been working for quite a few years now. We started in 2008 in this field. And basically, the conclusion is that you can substitute your diffuse scattering layer by a layer that is porous and that reflects light efficiently in the range that you want. And that range is the range in which your dye is absorbing. So this is the big difference with the diffuse scattering layer. If you put a diffuse scattering layer, everything is reflected back, no matter if it's interesting or not for your cell. In this case, you design it. You get a reflector that only gives you reflection at the spectral range in which the dye is absorbing. It's also a very thin layer, so it doesn't affect electrolyte diffusion. And obviously, we've been working a lot optimizing this flow of electrolytes through the mirror, so we get a very low resistance to this diffusion. And it offers also some other interesting possibilities, like changing the color of your cell, which is also a value if you think that every time, in general, these cells are an architectonical element at some point. So it's important to control how they look. Well, the effect was pretty clear in all cases. So for thin electrodes, you can increase a lot the efficiency of your cells. And obviously, the effect is smaller as you increase the thickness of your electrode. But you always see a clear change and a clear improvement in efficiency. Very recently, and I think this was practically our last work with this approach, we managed to create an aperiodic structure that is capable of reflecting the same spectral range that you can get with a diffuse scattering layer, except for the small window, a spectral window, that allows transparency to be preserved, right? So this is the result. So basically, you get something that is as efficient as the diffuse scattering layer, a little bit less always. And this is going to be impossible to beat, because diffuse scattering gives you oblique angles that always are better than specular reflection, right? But this is the closer you can get with a photonic crystal to the effect of a diffuse scattering layer, preserving transparency so you can still see through your cell, right? This approach, as I said, you preserve transparency, which is an added value of the cell. But there's something that is relevant too in this cell. The cell can be operated in a bifacial mode. So the original cell can be illuminated from frontal or from rear, and you can get an interesting value of the photocurrent. Once you introduce a diffuse scattering layer or a photonic crystal, the operation has to be just from the front, right? You cannot use illumination from the rear. So we started thinking about ways to solve that, and ways actually. So how to improve efficiency keeping the bifacial operation? The idea came to us because in a conference by Michael Gratzel, he mentioned that there are big plans in Arabic countries to install solar cells in the desert. And in the desert, you cannot install solar cells like that. You have to put them vertically. The reason is because it gets covered by sand very easily, right? So they were looking for ways for cells that were bifacial, and this is why he was involved in those conversations. So we tried to develop a method to improve the efficiency no matter what was the direction of light of incident light on the cell. And the approach just briefly, based on these photonic crystals, we work with a group of investors in Stockholm that finally made a company based on this photonic crystal approach. But this is something that is not related to what I was saying right now. This is what I wanted to tell you. If you use a texture surface it has a great advantage with respect to other approaches. Texture surfaces, first, you don't include any material. You just modify the texture of what you already have there, at least in this cell. I'm not talking in general. And when you have a texture surface, you can get something that is interesting, which is diffraction when you illuminate from the front. So you have this texture surface, and you will get reflected light in an oblique angle in the, when you illuminate in this mode. And when you illuminate from the back of the cell, from the rear, you get light in oblique angles in transmission mode. So you have a surface that provides you with two enhancement effects, different, but that helps to improve efficiency no matter what is the direction of light, right? And another interesting approach was actually coming back to the inclusion of diffuse scattering particles. What had been used in the past is to include particles that were very irregular, with a large size distribution and shape distribution. So they were polyhedrical rather than spherical. So we made an analysis of what would happen if you actually use spherical particles, thinking also in this bifacial operation, right? Because this is independent, again, of where the light is coming from. So we analyzed dielectric particles and metal particles, trying to see if metals actually could provide you something better than dielectrics. We found that it wasn't the case. So, and this is a little bit related to what I was saying before, that in this field, plasmonic particles, metal particles have been used a lot. There's no really significant improvement in efficiency. And even if there is a little bit, like you can see here, there's no point in dealing with all the hassle that you have when you put metals in a system, when with dielectric particles you can get much better results, right? So the scattering that dense titanium oxide or cavities, spherical cavities in the cell will provide you with is much better than the scattering, than the effect of gold or silver particles inside. Okay, basically once you do that, you can get a sort of design rule for disorder that I'm not going to be very specific about it, but basically what you can do is to kind of decide what is the right size of your particle and the right concentration, so your light gets randomized inside the cell. So you have your light coming into the cell, and it gets slowly randomized inside your electrode. And you want that randomization to take place in the length that correspond to the thickness of your electrode. So you can design that if you use spherical inclusions that you can actually model, right? So we are using here very basic Mie scattering theory, ray optics, and with that, you get a surprisingly nice match between the model and the experiment. And actually, you get a design rule, which is simply that you have to use a transport length, right, which is the distance at which you can consider your light randomized, that is slightly smaller than your electrode. Well, the other solar cell I wanted to discuss briefly about is the perovskite solar cell. This cell, as Ramon was saying before, has attracted a lot of attention lately. These are the two main designs of the cell that you will find, which is the mesostructure, in which you use a scaffold actually very similar to the one you would use for the dye-sensitized solar cells. In fact, some people still consider some versions of the perovskite solar cell as a dye-sensitized solar cell. There's a quite hot debate about it, actually. And the thing is that they have demonstrated that the cell works also nicely without the scaffold. And well, one of the questions here would be if the hype is justified. Well, at this stage, I think it is, because I don't think any other photovoltaic technology, and correct me if I'm wrong, has gone from 4% certified efficiency in 2009 to 20 in 2014. So this is a super fast. And I think even when you see the slope of the curve that you presented before, Ramon, in this NREL probably chart, show that clearly, right? So perovskite is going faster than any other. It has all possible problems. It degrades quickly. It has lead. So when it degrades, it releases lead. Terrible. Then all the record cells are half a centimeter times half a centimeter, and the typical problems of these new technologies. But it is true that I think the interest is justified because of this super fast development in terms of efficiency that is taking place. So something that we started working with here was, well, first of all, we wanted to see if there's anything to do in terms of the optical design, or so can photonics provide any help to this cell? The thing is that you have to, at the beginning I said, okay, the reason why we want photonics in photovoltaics is because we want to be able to absorb a lot of light in a very thin layer, right? The problem is that perovskite already has that. This is our starting point in the field. This is 400 nanometers, 500 nanometers, and basically everything is absorbed. So, but let's see anyway. There are always things you can do. So the first thing you need to do, as it happens in all, for all photovoltaic devices, is to have an optical description of your cell. You need to know if the basic design you are using is actually optimized from the point of view of optics, right? So this is what we started doing. This is a work we have done in collaboration with Henry Snaith. And we started with this cell structure in which we have the scaffold, in this case aluminum oxide, infiltrated with perovskite and a capping layer, which is schematized here. We obtained the optical constants, the real and imaginary part of the refractive index of flat layers, which actually it is not a simple thing to get, a flat layer of perovskite, right? Because it tends to grow in islands. But we managed to do that, and actually the optical constants we obtained fit very nicely all layers that we have been modeling. And we started describing what is the absorption profiles or the field distribution profile inside the cell. So you can see what you are looking at here, right? This is the different layers that you can find in a perovskite solar cell. This would be the glass. This would be FTO, and these are the scaffold with perovskite, the capping layer, the whole transporting layer. Okay. So basically, what you can see is that only in the very red part of the spectrum, the perovskite is not capable of absorbing efficiently, right? In the sense, we already knew that because you can look at the EQE. But there's something interesting that you get just from the optical design, which is an estimation of the internal quantum efficiency. It's something you cannot have if in your cell you have different materials that absorb, as it is the case, because the FTO absorbs, the whole transporting material absorbs, the gold absorbs, the back contact absorbs, right? So you need first to know in your model how much absorption is taking place in each part. And once you know how much is being absorbed by the perovskite itself, you can estimate what is your internal quantum efficiency. So this is the first thing you get from the optical description of your cell. Even if it's not an improvement, it's an important and relevant analysis you cannot do by any other means. Okay? Then, once you have that, you can think of optimizing the thickness of your layers so you can get a more efficient perovskite solar cell. Well, the effect, obviously we publish it, but it's not very relevant. What I mean is that once you have this typical thickness, 300 nanometers, 400 nanometers, and you change, for instance, the layer of your whole transporting material, well, obviously it is convenient to have a design so you use the thickness that provides you with the maximum, but the difference with the minimum is not very high, right? So it's not that you find a strong fluctuation. You're always fluctuating around a middle value that is pretty stable, okay? And this is basically the end of my talk. Just a picture of my group, quickly. Excuse me. As I mentioned before, I want to highlight that this work, in perovskite, was done in collaboration with the group of Henry Snaith, as part of the dye sensitized was done with a group of Janne Halme in Helsinki, or Juan Bisquert in Castellón, and our funding. And thank you for your attention.